show that f of x equals cos x is equal to its Maclaurin series expansion and find the radius of convergence. Hence, find Maclaurin series expansions for the following, including their radii of convergence. So that would be cos 2x and sine x. So to show that something is equal to its Maclaurin series expansion, remember that Maclaurin series expansion is going to be a series of ascending powers of x. So you've got a constant plus something times x plus something times x squared over 2 factorial plus something times x cubed over 3 factorial, and so on and so on and so on, all the way up to your nth term, which would be your something times x to the n over n factorial. So that is the sequence or the series upward for n terms, and then after that, remember, you have your error term. So basically, to show that something is equal to its expansion, you need to show that if you consider the error term, the limit as n approaches infinity of the actual error, you need to show that that equals 0, which would be enough to show that the Maclaurin series expansion and the actual function are equal, as long as there's enough terms, as n approaches infinity. So you have more and more and more terms. You're showing that the expansion actually is the function itself. Right, so we're going to do the expansion before we do any of this. Now, I know that the actual Maclaurin series for cos x is in the formula book, but I am going to do it the long way around. So we're going to need f of x, f dashed x, f dash dashed x. Evaluate them all at 0 because it is a Maclaurin series. Remember, a Maclaurin series is a Taylor series centered around x equals 0. So, f of x equals cos x. F dashed x is going to be minus sine x. F dash dashed x is going to be minus cos x. F dash dash dashed x, the third derivative, is going to go back to sine x. And now from there, so the fourth derivative, f4x, is just going to go back to cos x, and then we start the cycle again. So you're going to have cos x minus sine x, minus cos x, sine x, cos x, minus sine x, and so on. All right, so now we need to evaluate these at 0. So f of 0, well, it's just cos of 0, because f of x we said was cos x. Cos of 0 is 1. F dashed 0, or f dashed x, is minus sine x. Sine 0 is 0, so minus sine 0, also 0. F dash dashed 0 is going to be minus cos 0, so cos 0 is 1, so it's going to be minus 1. F dash dash dashed 0 is going to be sine of 0, which is 0 again. And then we know we go back to the cos of 0. So these derivatives are going to go 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on. So now we can say that, well, cos of x, which is f of x, equals, well, let's look at it. The Maclaurin series, it's f of 0, which is 1, plus, well, f dashed 0 is 0, so there is no x term, so we go straight to the x squared over 2 factorial term, and that's going to be f dash dash 0, so that's going to be negative, so it's minus x squared over 2 factorial, and then the same happens with the f dash dash dashed 0, that is 0 as well, so there is no x cubed term, so we go to the fourth derivative, and then we're back to 1, so that's going to be plus 1 times x to the 4 over 4 factorial. And now hopefully you can see a pattern. The next one's going to be negative, and it's going to be x to the 6 over 6 factorial. So now we need to try and actually define these using some kind of algebra. So basically, firstly, you can see that as the terms change sign each time, then we're talking about an alternating series. So that means you've got -1 to a power. So if we start with n being 0, so the first sign is positive. So if you have -1 to the power 0, that would give you 1, would give you a positive term. If n was 1, you would have -1 to the power 1, which will give you a negative. So plus, dot, 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 plus, so you've got -1 to the power n. Remember, this starts from n equals 0. So that's the bit that dictates the sign. And now we've got a power of x over a factorial. So if you think of 1 is x to the power 0. So if n is 0, you've got x to the power n there. But then if n is 1, we have x squared. Then if n is 2, we have x to the 4. So it's looking like you have x to the power of 2n. X to the power 2n. Remember, if we start with n being 0, 2 times 0 is just 0. So that works. That would give us an answer of 1. Think of the factorials. Well, they're exactly the same as the powers. And it does work for the first term because 0 factorial is 1. So we can say this is 2n factorial. Okay, so that is the nth term. Okay, and now we need to consider the error term as well. So we've got the series up until the nth term, but for this, because we've used this equals sign here, we need to actually include the error term, because for this Maclaurin series expansion to be exactly equal to the function, well, it needs to include the error as well. So remember, the Lagrange form of the error is, well, it's the next derivative evaluated at x equals c. C in this case would be between a and x, so a being 0 in this case. And then over, well, we've written n plus 1, n plus 1. If you look at the way it is, it's going to be 2n plus 1, because our nth term, we look at x to the power 2n over 2n factorial. So the next term, whilst you may be tempted to put 2n plus 2, because you're thinking, well, the powers are going up in odd numbers, that's how it works. Actually, because technically you're just dealing with this Lagrange form of the error, you need to be using 2n plus 1. So it's going to be plus the 2n plus 1th derivative, so f 2n plus 1 evaluated at a point C over 2n plus 1 factorial, and it's x to the power 2n plus 1. That is the error form. So now we've already touched it already, but the question is asking us to show that f of x equals cos x is equal to its own Maclaurin series expansion. Find the radius of convergence. We'll do the radius of convergence afterwards, but before that, to show that something is equal to its own Maclaurin series expansion, if I just draw your attention to this second point on Taylor's theorem, remember the only difference between Taylor and Maclaurin, that those two expansions, is that the Maclaurin series is centered at x equals 0 and the Taylor series is not. So it says f of x, as in a function of x, is equal to its Maclaurin series expansion if and only if the limit of the error term, Lagrange error, as n approaches infinity equals 0. So basically we need to look at this term and show that the limit as n approaches infinity of that term equals 0. Okay, so we are looking at the lim as n approaches infinity of f 2n plus 1 c, so the 2n plus 1th derivative, x equals c, x to the power 2n plus 1 over 2n plus 1 factorial. Now, if we just deal with the derivative bit first, basically, you know that f 2n plus 1 c, so the absolute value of that if you think about it, well, the derivative is either going to be, sine c, cos c, minus sine c, or minus cos c. So either way, the maximum absolute value of that is going to be 1. As sine c, the absolute value of that is less than or equal to 1, and also cos c, the absolute value of that is less than or equal to 1. So for that, 2n plus 1th derivative evaluates that c, we're just going to replace it with 1. So that's going to help us a lot. So now I'm going to look at the lim as n approaches infinity of the absolute value of the error term, x to the power 2n plus 1 over 2n plus 1 factorial. So if you think about that, well, n is only non-negative numbers, so the 2n plus 1 and the 2n plus 1 factorial will never ever be negative. Anything negative will only come from the x, so we can just put that absolute sign only on the x. So now we can turn this into the lim as n approaches infinity of, well, the absolute value of x to the 2n plus 1 over 2n plus 1 factorial. Now, the way to show that this is 0, so at the moment this is a sequence that we're finding the limits of. If we imagine it's a series, we can apply the ratio test, and if the ratio test shows convergence, then the limit of this must be 0. That's the way to approach it. So what we can do instead is find the lim as n approaches infinity of the absolute value of, remember it's an plus 1 over an. So we're going to apply the ratio test to see if a series like this would converge, and if it does, it means that this term must approach 0. Right, so this here, it's basically the 2n plus 1 is making the algebra difficult. So what we can do is if we let u equal 2n plus 1, now we have, as in for the limit as n approaches infinity of an plus 1 over an, we have the lim as, well, if you think about it, as n approaches infinity, u equals 2n plus 1 also approaches infinity, so we don't need to worry too much about that. So we have the limit as u approaches infinity of, well, it's going to be the absolute value of x to the u plus 1 over u plus 1 factorial over the absolute value of x to the u over u factorial. Remember, it's the absolute value of all of that for a ratio test. So now we can tidy this up, standard ratio test stuff. So this now equals the lim as u approaches infinity of the absolute value of, well, x to the u plus 1 can be x times x to the u. So you've got absolute value of x times x to the u over u plus 1 factorial. It can be written as u plus 1 times u factorial times u factorial times, remember, if you're dividing by a fraction, you can times by its reciprocal. So times u factorial over the absolute value of x to the u over absolute value of x to the u, and it's the absolute value of all of that. And to be fair, we don't even need that because all the x's are in absolute value signs anyway. So to be fair, it's not going to be negative if we keep these absolute value bits. Anyway, a bit of cancelling. X to the u, x to the u factorial. And now we can pull, we've only got this one x left, we can just pull that out. So we have the absolute value of x times the lim as u approaches infinity of, and it's just 1 on the top over u plus 1, 1 over u plus 1. As u approaches infinity, or as u approaches infinity, 1 over u plus 1 is going to approach 0. Okay, so now here we have, just put that in brackets, here we have the absolute value of x times 0 equals 0, right? So now remember what we're actually doing. We're trying to show that the series converges, which will show that the limit as n approaches 0 of the error term must equal 0. So the ratio test, remember, it shows convergence if the result is less than 1. So the result is 0. So that definitely shows convergence. And remember what we're actually trying to show converges. It is this absolute value of x to the 2n plus 1 over 2n plus 1 factorial. So the series from n equals 0 to infinity of the absolute value of x to the 2n plus 1 over 2n plus 1 factorial, we've just shown that that converges. And that was the ratio test. It's actually a very useful result. So basically, if you have any series that is the absolute value of x to a power over the same power factorial, that will always converge. And the ratio test is the way that you show it. So the lim, because this converges, obviously, as the sequence, as the term number reaches infinity, the actual terms in the sequence must get closer and closer to 0. Because if they didn't, then how could the series possibly converge? So the limit as n approaches infinity of this as a sequence, so just x, absolute value of x to the power 2n plus 1 over 2n plus 1 factorial must equal 0. For series to converge. Okay, so now just remember where we're at, because this is quite a long problem. We have just shown that this error term, as n approaches infinity, we've shown that this approaches 0, which is enough to show, as is on here, it's enough to show that f of x, which is cosine x, equals its own Maclaurin series of expansion because the error term approaches 0 as you get more and more and more terms. So therefore, cosine x does equal the sum from n equals 0 to infinity of, remember how we defined it? It was minus 1 to the power n, x to the 2n over 2n factorial. Over 2n factorial. And then if you think about the actual radius of convergence, so if we were to kind of do another ratio test, well, we've already done enough really. The minus 1 to the n bit just affects sign, and it would disappear when we did the ratio test anyway. Then we would just be finding the limit as n approaches infinity of x to the 2 brackets n plus 1 over 2 brackets 2n plus 1 factorial. And so if you think about that ratio test, if we were to just apply it on this bit, it wouldn't be any different. It would converge. If we were to apply the ratio test to that series, the result would be 0 again, because always, so if you have a series from n equals 0 to infinity of some x to the k over k factorial, that will converge everywhere. So if we take it as an absolute, that will be absolutely convergent everywhere. The ratio test will show you that, so we've just really done the ratio test to prove it. This converges for all real x. So if it converges everywhere, then the ratio of convergence must be infinite. Ratio of convergence is infinite. We probably should just specify that k needs to be a positive integer, but it wouldn't work if it wasn't anyway. So now finally we can move on to part B. Hence, find Maclaurin series expansions for the following, including their radii of convergence. So we've got cosine of 2x and sine of x. So basically, to do B, I think I'm just going to write the actual cosine x. Remember, cos x equals, well, it was 1 minus x squared over 2 factorial. So 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus dot 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 plus minus 1 to the n x to the 2n over 2n factorial. And we know that that is the exact expansion because we've done all the stuff with the error term. So for cos 2x, all we need to do is just replace the x with a 2x. So it's going to be 1 minus 2x squared over 2 factorial plus 2x to the 4 over 4 factorial plus dot 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 plus the minus 1 to the n bit's not going to change, but then we're going to have 2x to the power 2n over 2n factorial, which also isn't going to change, only the x bit. So if we write that as a series, well, that's going to be the sum from n equals 0 to infinity of minus 1 to the power n, 2x to the 2n, all over 2n factorial. So that was B1. Oh, we need to state the radius of convergence. It's not going to be any different for exactly the same reasons. Once we, if we did the ratio test on that, it would again equal 0. So radius of convergence is infinite. Infinite. And if we now look at the last piece, we need to do the same with sine x. Now that is different. So basically, the best way to do this is to use our result for cos x, and it's actually quite fun to do. So we know that cos x, I'm just going to write it out again because I'm going to move. We know that equals 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot dot dot. So now, if we want to turn this into sine x, well, think, well, what happens when you differentiate cosine x? It goes to minus sine x. So if we think of this as an equation, as in left-hand side, the cos x equals right-hand side, the expansion, well, then we can say we differentiate both sides with respect to x. This would be minus sine x, which is very close to the thing that we want to find, equals, well, we now just differentiate term by term with respect to x. So the 1 will disappear. The minus x squared over 2 factorial is going to be 2x over 2 factorial. And it's still going to be a minus sign. The next term, it's all going to be positive, and it's going to be 4x cubed over 4 factorial. And the next term is going to be negative, and it's going to be 6x to the 5 over 6 factorial, and so on. So then, if we can tidy this up quite a lot, well, 2 over 2 factorial, well, 2 factorial is 2, so this is just minus x. So minus sine x equals, well, it's minus x. The next one, if you think about this 4 over 4 factorial, that's 4 over, or 4 factorial could be written as 4 times 3 factorial. So 4 over 4 times 3 factorial just leaves you 1 over 3 factorial. So that would be plus x cubed over 3 factorial. The next one, you've got minus 6 over 6 factorial. So 6 over 6 factorial, that's the same as 6 over 6 times 5 factorial. Again, cancel, we just end up with minus x to the 5 over 5 factorial. So then we have an expression for minus sine x. To turn that into sine x, you can just times by minus 1 or divide by minus 1, whichever way you want to look at it. So that would say sine x equals, well, it's going to be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and then plus dot, dot, dot. So to define this using an nth term, it gets tempting to start from n equals 1, because we know that the nth term of the odd numbers, if you start from n being 1, is just 2n minus 1. So, but if you want to have the same sort of definition as in from n equals 0, well, if you consider n being 0, then I want the power to be 1. So if I'd say 2 times 0 would still be 0, then add 1, that would get 1. If n was 1, or 2 times 1 plus 1 would be 3. If n was 2, 2 times 2 plus 1 would be 5, and so on. So you could say it's going to be x to the power 2n plus 1 if you start from 0 over, the factorials are the same as the powers anyway, so 2n plus 1 factorial. And the signs, well, if you look at the signs, the first term is positive, negative, exactly the same as the cosine bit, so it's just going to be minus 1 to the n again. So you could say sine x equals the sum from n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And for the same reasons we've already discussed, if you were to do the ratio test on that series, it would have a value of 0, and it wouldn't matter what the value of x was, so it converges everywhere. The radius of convergence is infinite. Okay, so infinite radius of convergence on all 3 series.